So, welcome back to our course on blockchain. So, in the last class we were discussing about the consensus algorithm for permission blockchain environment in a generic distributed system, and we have looked into the concept of Byzantine general problem and how can you achieve consensus in a synchronous environment with the Lamport's algorithm. So, in that particular algorithm we have seen that if you have f number of lieutenants faulty, then with 2f plus 1 number of lieutenants in the system, you will be able to achieve consensus in the system. Otherwise, if the commander is faulty, in that case also with 2f plus 1 number of lieutenants, you will be achieved to reach consensus within a synchronous system. But as we have mentioned earlier that our real systems are not always synchronous. The real systems behaves in an asynchronous way where there is no guarantee that you will receive a message within certain timeout duration. So, in this class we will look into that how can you still achieve consensus, or at least you will be able to ensure the safety property of a consensus protocol in the presence of faulty nodes. But remember that in an asynchronous environment we have the impossibility theorem that states like in a pure asynchronous environment, if you have at least one number of nodes are faulty, or if you have even a single faulty node, it is impossible to reach into the consensus. So, that is why in this consensus algorithm that we are going to discuss, which we call as the practical Byzantine fault tolerant consensus algorithm, for ensuring the safety property we consider a complete asynchronous system or a pure asynchronous system, but we cannot ensure the liveness property because in that case it will violate the impossibility principle. So, that is why to ensure liveness we relax the asynchronous nature or asynchronous guarantee of the system, and we will see that well with certain relaxation in the asynchronous condition which we call as a weak asynchrony in the system. So, with weak asynchrony in the system, which is not a pure asynchronous system, but a relaxation on the asynchronous system, we will be able to ensure safety all the time, and we will be able to ensure liveness for most of the time. So, let us look into this algorithm which we call as the practical Byzantine fault tolerant or PBFT algorithm. So, this algorithm is termed as practical because it ensures safety over an asynchronous network, but not liveness on a pure asynchronous network. Otherwise, it will violate the impossibility theorem or the impossibility principle. So, to ensure liveness we have a weak asynchronous assumption where we deviate from a pure asynchronous system. I will discuss all this construct in details. Then the system is able to support Byzantine failure and it has low overhead. So, that is why we call the system as an asynchronous system. Now, this PBFT algorithm, it is applied for many real applications. It is widely applied for the permission blockchain model like this Tendermint, IBM's OpenChain, Hyperledger, this kind of platform which uses permission blockchain environment. So, to ensure consensus among the participants in a closed environment, we apply this kind of PBFT type of algorithm. So, we will go to the details of this PBFT algorithm. So, here also we are having this Byzantine model, the Byzantine fault tolerant model. So, the broad idea of the system is something like this. So, in this system there is a client, the client submits the request to the commander. So, here the client, if you think about from the blockchain principle, the clients are the individual blockchain clients who are submitting the transaction, and the commanders are certain nodes in the system who are responsible for ensuring consensus in the system. And you have multiple nodes. So, this commander in cooperation with the multiple nodes in the systems that have been shown here using blue lines. So, with the help of these multiple lieutenants in the system, the commander come to the consensus, and once the system comes to the consensus, it sends a response back to the client whether the system has committed based on the consensus algorithm or not. So, you can map this entire principle in a blockchain environment where the client submits a transaction and there are certain nodes in the network who are designated for running the consensus algorithm. Those nodes collectively design the consensus algorithm or run the consensus algorithm, and they decide whether the transaction can be committed or not. If the transaction can be committed in the system, then that response is sent back to the client. So, that way this entire system works. Now, as you have assumed that it is a asynchronous distributed system. Because it is an asynchronous distributed system, you can have delay in transmitting the message, and you can also receive out of order messages. Then the system can have Byzantine failure, like the arbitrary node behavior. So, some nodes can vote for a transaction and against for a transaction. Additionally, this PBFT algorithm, it also supports privacy over the system. So, it ensures that the messages are tamper proof. It applies a hashing technique similar to blockchain. We will discuss that in details, and it also applies the authentication technique through this digital signature mechanism, so that none of the messages transferred from individual nodes in the system can be tampered or can be eavesdropped. So, that is the system model. So, we consider a state machine, a replicated state machine concept that we discussed earlier in the context of distributed consensus. So, we have a state machine which is replicated across different nodes, and we have 3a plus 1 replicas. So, this number is important where we are deviating from our consensus algorithm in a synchronous environment. So, what we have seen that in a synchronous environment, if you have number of faulty nodes, then you require 2a plus number of lieutenants or 2a plus number of nodes apart from the commander to ensure consensus. But in case of a asynchronous network, we require 3a plus 1 replicas. But why do we require 3a plus 1 replicas? At a point while we will discussing about the algorithm, I will discuss about this particular assumption, that to ensure f number of faulty replicas, why do we require 3a plus 1 number of replicas, which will ensure you having consensus in the system. Now, these replicas, they move through a successive of configuration known as views. So, these views are something like that. Among this set of replicas, if you try to map it in a Byzantine general model, we have this commander and we have individual lieutenants. So, similarly, we have among these replicas, we have one primary and multiple other backups. So, that way this setup of primary and the backups, we consider them as a single view. So, assume that you have 4 different replica here, and among these 4 different replicas, you have this replica which has been designated as a primary replica, and others are designated as a backup replica. So, this replica takes control of the state machine, and these other replicas stored a backup of the state machine. Now, this particular set of configuration, that we call as one view. Now, in different views, the primaries and the backups can change. It may happen that in a different view, so in a different view, this primary becomes primary becomes a backup, and another backup becomes a primary. This is a second view. So, that way the replicas, they move through a successive set of configurations which are known as views, and one replica in a view is primary and others are known as backup. So, these views are changed when a primary is detected as faulty. So, whenever the backups, they collectively detects that a primary is faulty, we will look into this view change mechanism, then these views are changed, and every view is identified by a unique integer number v, with a unique integer number v, and only the messages from the current views are accepted. So, if there is a view change, then the messages which have been broadcasted in the previous view, and because of the asynchronous nature of the system, it may always happen that you are receiving the message, a delayed message or out of order message, and you are receiving message from a previous view. So, the messages from the previous views are discarded and only the messages from the current views they are accepted. So, let us look into a simplified view of this PBFT algorithm. So, this PBFT algorithm was proposed by Castro, Miguel and Barbara Liskov, that was first came into OSDI in 1999, and the title of the paper was Practical Byzantine Fault Tolerant. So, I suggest all of you to read this paper in details. So, the idea of this algorithm is as follows. So, the client send a request to the primary. So, the client executes some kind of service operation, like in case of your shared storage, the client executes a write instruction, or in case of a blockchain environment, the client initiates a transaction. So, all these client requests, they are moved to the primary. Then the primary, it sends this request to all the secondary replicas. So, this primary, it multicast a request to the backup. So, these backups are the secondary replica, whatever you call it. So, this information is sent to the backups. Then these backups, they execute the request, and they try to come to the consensus based on this PBFT algorithm that we will discuss shortly. So, after executing the request, either the client request is successful or the client request is failure. So, for example, in case of a shared storage architecture, if the client is trying to initiate a disk write operation, either that disk write operation was successful if it is able to write that instruction correctly into every individual replica, then it is successful, otherwise it will be a failure. Similarly, for the blockchain perspective, a transaction, if it is a valid transaction, if all the backups or all the replicas decide that the current transaction is a correct transaction, then it sends a success or a commit message to the client, otherwise it will send a failure message to the client. So, the backups, they will execute the request and accordingly send a reply to the client. So, the client will receive all these replies. Once the client receives all the replies, so the client basically waits for a plus number 1 of replies from different backups with the same result, where f is the maximum number of faulty nodes, faulty replicas that can be tolerated. So, once the client receives a plus 1 replies from different backups with the same result. So, these keywords are important, that the client need to receive a plus 1 replies from different backups and the results are same. That means, the client can decide that it has got majority of the correct voting. So, remember that you have in this PBFT algorithm, you have 3a plus 1 number of different replicas. So, out of this 3a plus 1 number of replicas, you have f number of replicas which are faulty, but whenever the client is receiving the message, if it gets a plus 1 message with the same result, that means the majority of the nodes, here actually not the majority of the nodes, the correct nodes, majority of the correct nodes, they are sending a reply to you. So, when majority of the correct nodes are sending a reply to you, then you can say that well the system is reached to a consensus and the client accept or commit that particular message. So, in other words, you have 3a plus 1 number of replicas in the system, out of f number of replicas are faulty and 2a plus 1 replicas are correct. So, if you are receiving a plus 1 replies from different backup with the same result, then you can be guaranteed that well you are receiving a result which belong to the majority of the correct replicas. So, if you receive a message from majority of the correct replicas, you can assume that message to be the consensus message and you can include it include it to your system by committing that particular request. Okay. Now, this entire consensus algorithm in PBFT, it works in 3 different phases: pre-prepare, prepare and commit. So, we will look into these 3 different phases in details. So, in pre-prepare phase, the primary, it assigns a sequence number. So, initially the client has sent a request to the primary. Once the client has sent a request to the primary, then this pre-prepare phase starts. In the pre-prepare phase, the primary, it assigns a sequence number n to the request and multicast a message called pre-prepare along with certain parameters to all the backups. So, let us see what are these parameters. So, here V is the current view number. So, you are ensuring that the message that you are going to receive, it is from the current view. Then n is the sequence number, n is the message sequence number that the primary has included in the message. D is the message digest, and this entire thing, entire pre-prepare message, it has encrypted with the primary key, with the private key of the primary. Now, if you remember the digital signature method that we have discussed during the first few classes. So, whenever A is sending certain messages to B and A has its own primary key, say sigma A is the primary key for A and say pi A is the public key for A. So, A has 2 different key, one is a private key, another is a public key. So, A can encrypt a message. So, it can encrypt a message with this private key, and at the other end B can decrypt this message with the public key. Now, this particular mechanism works like a digital signature, and it ensures that whatever message you are receiving from A, that message has actually originated from A. So, with this architecture, this digital signature architecture, you ensure that this pre-prepare message is actually coming from the primary, because it is encrypted with the private key of the primary. And here we put the message digest, because if you again remember the digital signature method, rather than putting the message here, because the message size is long, we apply the hash based technique to reduce the message size, and rather than putting the message, we put the message digest. Say MD is the digest of the message, which is encrypted with the private key of primary. So, the similar concept is applied here with the message that we are transmitting here, the message M. You also transfer the message digest and the entire thing encrypted with the private key of the primary, so that all other backups, whenever they will decrypt this message with the public key of primary, they will be able to know that this particular message has been originated from primary and it corresponds to the message which has been sent. So, this is the pre-prepare message that is sent by the primary to all the backups after assign the sequence number n. So, that is the thing in pre-prepare. So, once the client sends the request, then in the pre-prepare message you broadcast this pre-prepare message to all the secondary. So, here in this example we are assuming that one secondary is faulty. So, we have 3f plus 1 number of different replicas. So, we are considering here f equal to 1, we have one faulty replica which is S3. So, we have a total of 4 different replicas, so 1 primary and 3 backups. So, in the pre-prepare phase, the client assigns a unique sequence number to the request message and broadcast that request message to all the replicas. The second phase of the 3-phase commit protocol is the before going to the second phase of the 3-phase commit protocol. So, in the pre-prepare phase, so these pre-prepare messages, they are used as a proof that the request was assigned a sequence number n in the view V. So, the message is in the current view and it has been assigned a unique sequence number. Now, a backup, it accepts a pre-prepare message if the signature is correct, and D is the digest for M to verify the digital signature that it has been originated from the primary. The backup is in view V, so you are in the latest view. It has not received a different pre-prepare message with the sequence number end and view v with a different digest. So, that means the message has not been tampered. If the message has been tampered, that means the digest would be different, and the sequence number is within a threshold. So, it also ensures that these sequence numbers are not too old, such that there is no kind of replay attack in the system. So, an attacker is not getting that message or just capturing the message which was being transferred by the primary and replicating it after some time. So, it is not a replica. So, then the backup accepts a pre-prepare message. The second phase is the prepare phase. In the prepare phase, this secondary it sends a prepare message to all the replicas. So, let us look into this prepare message in details. So, if the backup it accepts the pre-prepare message, then it enters this prepare phase, and in this prepare phase it multicast a prepare message. So, the prepare message all has the similar set of parameters which were there in the pre-prepare phase, the view number, the sequence number of the message digest, along with the identity of the backup which is broadcasting this prepare message, and the entire thing is encrypted by the private key of the backup to ensure it as a digital signature, and this prepare messages is originating from backup I. So, that is the prepare message which has been broadcasted in the prepare stage. So, a replica, the replica here can be a primary as well as backup, it accepts the prepare message if the signatures are correct. So, it is coming from the intended backup, the view number it equals to the current view. So, the message is in the current view, and the sequence number is within a threshold, the sequence number is not too old. So, it is not a replica. Now, these two stages, the pre-prepare and prepare, they ensure that non-faulty replicas they guarantee on a total order of the request within a view. So, it is like that every individual request they are assigned one sequence by the primary. So, once the primary assigns a sequence to individual messages or individual transactions which are coming from the client. So, all these messages are ordered based on the sequence number which is assigned by the primary. So, all the backups they process the messages in the order of that sequence number. So, if a sequence number has along with if a sequence number is higher than the current sequence number, then that one is processed first. So, in that order of the sequence number the messages are being processed. So, after this prepare and the pre-prepare stage, once every replica gets this prepare message, then it commits a message if 2F prepare messages from different backup it matches with the corresponding pre-prepare. So, whatever has been transferred in the pre-prepare message, you have received the prepare message with the same message and the same message digest, and it is coming from at least 2F number of prepare message. So, you have received 2F such message. So, here you have a total of 2F plus 1 votes that you have received in total. 1 vote is from the primary and that you already have, and you have got 2F number of votes from other replicas. So, if you remember that whenever you are waiting for this kind of vote. So, here in this context, in this context let us discuss that why do we require 3F plus 1 number of replica to ensure safety in a asynchronous system when there are F number of faulty nodes. Now, here the thing is that if you have 2F plus 1 replica, to have a majority decision you need to ensure that you have received all the votes, and out of all the votes at least F plus 1 votes are giving the majority decision. So, to take a majority decision with 2F plus 1 number of replica, you need a vote from all the replicants. So, this boils down to a synchronous environment where you need to wait to get the message from all the replicas. Now, in case of an asynchronous system, you may not receive the votes from certain replicas because of the delay, or you may receive out of order messages. In that case, if you just receive a plus 1 vote, so that a plus 1 vote does not ensure majority. So, if you receive continuous a plus 1 vote and that a plus 1 vote are giving you the same instruction or the same information, then you can accept that vote, but it may happen that out of this a plus 1 vote, certain votes are coming from the faulty nodes. So, you do not know whether those votes are coming from the faulty nodes or from the correct nodes. So, whenever you have received certain f number of votes, those f number of votes may be coming from the faulty nodes, and all the faulty nodes are behaving equally, and they are possibly saying in the Byzantine general problem, say they are saying about retreat. Now, if you get retreat message from f number of nodes, you really do not know that that f number of nodes are faulty, or some other nodes are faulty, or they are correct. Now, say you have received f retreat message, and after that you have received one attack message. Now, if you receive f retreat message and one attack message, you cannot be sure that whether those f number of votes that you have received, those are from the normal node or from the Byzantine nodes, because you know that there are f number of faulty nodes in the system. And this is an asynchronous system. Because this is an asynchronous system, it may happen that you have also not received certain votes. Now, to ensure this, whenever you are not receiving a vote, it may happen that that particular node is faulty and it has not forwarded a vote at all. So, a faulty node here has the option that it will not forward any vote because it is an asynchronous system. Either that is the option, or the second option is like the node is non-faulty, the node is a correct node, it has sent you a vote, but that vote is tracked somewhere in the network. So, you have not received that vote. So, that can be the situation where the vote got delayed. But if you receive 2a plus 1 vote, and whenever you have received 2a plus 1 vote, and if you see that, well, out of the 2a plus 1 vote that you have received, out of them a plus 1 are in the majority. If that is the case, then you can guarantee that, well, whatever the majority vote says out of the 2a plus 1 vote that you have received, that is the consensus. So, it is like that. To have the consensus in the system, you can have 2f plus 1 number of correct nodes and f number of faulty nodes, because you may not receive the votes from certain number of correct nodes, and you can tolerate such nodes, or you can tolerate such kind of votes after up to f number of times, because you can have f number of faulty votes. So, whenever you are receiving the first f votes, you do not know whether those first f votes are coming from a correct node or from a faulty node. So, that is why we require 3a plus 1 number of different replicas in a system, where f number of replicas are faulty replicas and 2a plus 1 number of replicas are correct replicas. In that particular case, if you are receiving a plus 1 votes and that a plus 1 votes are saying the same thing, like all the a plus 1 votes are saying that attack, then you can decide anonymously that, well, in your system there can be f number of faulty nodes. So, what a plus 1 votes you are getting, that gives you a kind of correct result or a majority result, because that is going to be said by all the correct nodes. So, to say it in other word, if you are getting a plus 1, say a plus 1 number of votes, and all the a plus 1 number of votes are attacked. So, out of this a plus 1 number of votes, you know that f number of votes can be faulty. So, even if out of these a plus 1 attack votes, f votes are coming from the malicious or the Byzantine nodes, and you do not able to predict that what the Byzantine nodes are going to say, there is at least one node which is in the for of attack, and it is a non-faulty node. So, if it is the vote for a non-faulty node, then all the non-faulty nodes in the system, they are going to vote for attack. So, you can correctly decide that attack is your final consensus value. So, that is why we require 3f plus 1 number of replicas to detect f number of faulty nodes. Well, at the end, every node multicast the commit message to all the replicas include primary. So, whenever you have received 2f plus 1 number of such commit messages, from that 2f plus 1 number of commit message, if f plus 1 from the majority decision, it can decide that whether the transaction has been accepted or whether the right instruction that request that has been sent by the client, whether that request has been accepted or not, because you are getting on that majority voting. So, that is the final commit message. After final getting the commit message, every individual node takes its decision and it sends the reply back to the client. Now, let us look into the case that when the primary is faulty. So, if a secondary is faulty, so we have seen that we can tolerate up to f number of such failures, and within this f number of failures, if f number of secondaries or the backups are faulty nodes, the system can tolerate that, but what if the primary is faulty? Now, in that case, the non-faulty nodes, they detect the fault. So, the backups, they detect the fault collectively and they together start a view change operation. So, they remove the primary from the system, or they consider that the replica which was designated as the primary in view V, that will get changed, another replica from the backup that will be designated as the primary. Now, this view change protocol, it ensures liveness, but to ensure this view change, you have to ensure that you will receive the message from all the nodes within a timeout duration. So, here comes the weak synchrony assumption in the system, like to ensure the safety, you do not require a synchronous assumption, but to ensure the liveness, to ensure that the view change are done at a proper time interval, you have to ensure that all the backups, they are able to detect that the primary is not sending any message within some timeout duration. So, whenever you are putting this kind of timeouts in the system, so here we put a timeout in the system. When you put the timeout in a system, you have an assumption that if you are not receiving the message within this duration, then you are considering that message to be lost and the primary to be faulty. So, here we are deviating from the pure asynchronous assumption. So, the pure asynchronous assumption says that your transfer of message can be arbitrarily delayed, but here we are assuming that it is not truly arbitrarily delayed to ensure liveness. Rather, to ensure liveness, you have certain level of synchrony if you are not receiving the message from the primary. So, this primary to secondary communication, it is a synchronous communication. If you are not receiving the message from the primary within a timeout duration, you assume the primary to be faulty. Okay. So, these backups, they starts a timer when it receives a request and the timer is already running. So, the timer is stopped when the request is executed. So, within that timeout duration, everything is complete and the timer gets restarted when some new request comes. So, when some new request comes, you just look into whether you are receiving the messages from the primary within that timeout message or not. Now, if the timer expires at view V, then the backup starts a view change to move the system to another view V plus 1. So, on timer expiry, a backup stop accepting any new messages except the normal checkpointing message, the view change message and the new view message. So, only view change is being performed during that time. Now, this view change operation is little straightforward. So, when a primary has a timeout, it multicast a view change message to all the replicas along with certain option. So, it initiates a view change for a new view V plus 1 along with the sequence number of the last table checkpoint. That means, it is the sequence number of the last transaction that is being accepted, and then certain sets. So, this C, it is a set of 2f plus 1 valid checkpoint messages it proved the correctness of this S, the correctness of the checkpoint. So, it ensures that the last checkpoint that this particular node has received, that particular last checkpoint is a correct checkpoint. So, that was based on the normal PBFT safety algorithm. So, this ensures the safety criteria of the system. And this P, it is a set containing another set PM for each request M that prepared at I with sequence number higher than n. So, it ensures that well certain number of request messages are still flowing in the network, but you want to initiate a view change. So, whenever you want to initiate a view change, you also embed the request message which have been initiated in the previous view, but that has not yet committed, because once the view change is being done, then those old messages need to be taken care of. So, because of that, this particular set P, it embed all such old requests. So, each set PM, it contains a valid pre-prepare message and 2F matching of that pre-prepare message. So, a new view, it is initiated after receiving 2F number of view change message. So, among you know that in the system you had 3F plus 1 number of total number of nodes, out of them F are faulty and the primary has also observed a fault. So, in that case if you receive 2F plus number of view change message, so it is like that 2F messages are received from the correct replicas. So, a view change need to be initiated. So, this view change operation, it takes care of the synchronization of the checkpoint across replicas. So, that synchronization part I am not going to the details, rather keeping it as a take home assignment for you to read the PBFT paper and to understand this part, that the view change operation, it takes care of the synchronization of the checkpoint. Like it may happen that well certain whenever you are sending the view change message, due to the asynchronous nature of the system, certain nodes they are still in their pre-prepare or the prepare state, and they will also be able to get the correct checkpoints, and it ensures that all the replicas they are ready to start at the new view at view v plus 1 when the primary has changed from the old primary to another primary. So, the safety property of the algorithm. So, the algorithm it provides safety if the non-faulty replicas they agree on the sequence numbers of the request that commit locally. So, we have observed that if you are receiving a plus 1 number of correct messages or a plus 1 number of messages from the correct replicas out of 2a plus 1 message that you are going to receive, if all the replicas relies on the latest sequence number, then that part get committed. So, only the latest sequence number will get committed in the system that ensure the safety criteria. And the liveness criteria, to ensure the liveness criteria, we need to ensure that whenever there is a fault in the primary, the system moves from one view to another view. So, in that particular case, a replica it waits for 2a plus 1 view change messages and then starts a timer to initiate a new view. It avoids starting a view change too soon. If you start a view change too soon, then a faulty replica may just initiate a view change very periodically, and it will hamper the liveness of the system. The system will not be able to progress if there are frequent view changes. So, to prevent frequent view changes, we ensure that once you are receiving sufficient number of view change requests, then only you change the view from one node to another node by ensuring that the primary is faulty. Now, again you have to ensure that the view change are not delayed too much. If the view change are delayed too much, then also it will affect the liveness property. So, if a replica receives a set of a plus 1 valid view change message for the views greater than its current view, then it also initiates a view change. So, it is like that the view change are initiated for two different conditions, either a timeout occurs. So, you need a plus 1 different timeout to occur, otherwise you receive a plus 1 number of different view change message, and once you are receiving a plus 1 different view change message, you also initiate a view change operation. And this way the faulty replicas, they are unable to impede the progress by forcing frequent view change. So, even if you have a faulty replica in the system, you cannot have very frequent view change in the system. So, look into the further details of this paper for the theoretical proof of PBFT, and as we have mentioned that this PBFT, it has well adapted for consensus in permission blockchain environment like Hyperledger and Tendermint. And well, many of the scalability issues are still there because it is an open environment and every node need to send that multicast message to every other node in the prepare and the commit message. So, the system has a high message complexity, because of which you have scalability issues. So, in the latter part of the lecture, we will look into the scalability issues in details and look into several optimization on top of the PBFT protocol, which have been adopted by the blockchain researcher. So, this gives us a broad idea about the permissionless blockchain and the permission blockchain model and different type of consensus protocols which are there. So, from the next class onwards, Praveen will be taking the classes and he will look into the practical aspects of Hyperledger and different implementation details of blockchain along with the industry use cases. So, I will be back after few lectures from Praveen, and again discuss about the various use cases and research aspects which are there in the blockchain domain on which we are exploring currently. So, hopefully, you will be enjoying the practical aspects of blockchain or the implementation details of blockchain and the corresponding demos that will be shown by Praveen from the next lecture onwards. We will come back again after those demo sessions. So, thank you again for attending. We will next look into different use cases of blockchain. Thank you.